Okay, good morning, everybody. Just a quick check, can you hear me? Cool. So I don't actually have any announcements to start with. So I thought we would jump right into any questions you have about the homework that you went over, upcoming homework and lab, like lab 3 and homework 3. Okay, first question I see, could you go over written homework question 3C? Let me bring it up and we'll take a look. So homework 3, written homework 3, problem 3C, the whole of problem 3 talks about catenaries. So let's set it up. You're given an equation like so. And from this, you're asked to make a substitution, which is v is equal to dy dx. I'll color this, let's say, a magenta here. And now if we think about substituting this back into the differential equation, well, we can just straight substitute it into there and get 1 plus v. And then over here, we can substitute if we take the derivative of v. So the derivative of v with respect to x is the second derivative of y with respect to x. Now do the substitutions, namely we're going to let this be the green part and then this be the magenta part. And making those substitutions, we now have, I'll just write v prime for the moment. That's the green part, is equal to this set of constants times square root of 1 plus v squared. And then you're asked to classify this result. And if you think about the terms that we've learned, such as linear, linear homogeneous, nonlinear homogeneous, what other things? Separable, exact, and so on. If we look at this now, well, I don't think it's linear. The dependent variable is v, but we have a v squared here. So that says it's not linear. But another good one to check is whether it's separable. And I think it is separable. Namely, we can take and rewrite it as dv dx is equal to all these constants here times this 1 plus v squared, and then divide appropriately. And considering these to be constants, now we have a separation like we see here. So it is separable, not linear, but separable. And other things might include Bernoulli, but it's not Bernoulli because in order to be Bernoulli, you have to be essentially really close to linear, but we're not that. You could check exact, and I think I've mentioned this to some students, but maybe not all. I can't remember if I've mentioned this publicly, but you'll see in a homework assignment, if you haven't already, I can't remember if this has come up yet, but in fact, if you're separable, you are exact, or if you have an equation that's separable, you're exact. So separable implies exact. So since since this differential equation is separable, then it's also exact. And since it's not linear, we can right away say that it's nonlinear. You're either one or the other. And there is another criteria, since we only see the dependent variable, that means it's also autonomous. The only other thing that I can think of offhand is the order, and of course it's first order. There may be one or two other that I'm forgetting. I would check over all the terms that we've gone over, but that is most likely a complete list, but at least gives you an idea of what's going on with this problem. And let me see if there's another part to it. And then once you've classified it, you can use the techniques. So once you know that it's separable, you can use separation of variables. You could even use finding potential function because it's exact. And that's really it. So in this case, you can use separation of variables, find a general solution. And that's all there is to that problem. The next question that someone asked was, can you do the first problem from the daily homework from yesterday? Yeah, I can look over that. Let me bring it up. So this would be day 12 online homework. This would be number 1. Or at least I think it'll be number 1. Some of these, they mix up the order. That should only be the setting for the exam and maybe the review, but some of the online homeworks might have mixed up. So we each have different question 1s. But what I have for a question 1 is, let's say, 2y double prime minus 5y prime minus 12y is equal to 0. And then I have y of 0 is equal to 1. Y prime of 0 is equal to negative 12.5. And then the first thing that's asked is, does the second order existence and uniqueness theorem apply? And if we look at this, for that theorem to apply, we need there to be an interval around 0, since that's the point that's part of the initial value data, such that all of these functions are continuous around there. But since they're all constant functions, they're going to be continuous over every interval. In fact, the whole real line. So indeed, it will apply. So let me highlight these. What we do is we want to say it a little bit differently. We actually want to divide by 2 first, so that we have a 1 here. But nonetheless, these are still all constants. And just to be careful, it's important that they're continuous, not constant on the interval. But since they're constant, it gives you that they're definitely continuous. So if you look over the, let's say, real line, and you look at the value 0, which, let me try to highlight this. Put this maybe in, how about this red here? Then if we look at 0, it doesn't matter what the interval is. Pick your favorite interval, maybe negative 1 to 1 is plenty. And you look at each of those functions, they're all constants. So they'll be continuous, just different, levels of constant over that. And since they're all continuous, then the theorem would apply. The second part then is to say, now that you know that a unique solution to the initial value problem exists, use the characteristic polynomial to find it. So in this particular case, you would look at, and I am going to move this to another page now that we've done that first part. I'm actually even going to rewrite it. Either way will work, but. And if we factor this, or rather we look at the characteristic polynomial and then try to factor, we'll be able to find what the roots are, and then that'll tell us what the solution looks like. So the characteristic polynomial is 2r squared minus 5r minus 12. Now, once you have a quadratic, you can use the quadratic formula. Sometimes you can right away see how to factor it, and maybe this one, it's obvious to you right away. I don't necessarily see it and don't want to just stare at it for a while not talking, so let's do the quadratic formula. So we have the roots are negative b, which is 5, over 2 times a, which would be 4 in this case, plus or minus, again, 1 over 2 times a. Then we have 25 minus 4 times a times c, which will give us 5/4 plus minus 1/4. And let's see, 25, 8 plus 8 times 12, which is 80 plus 16, 25 plus 96, which if we add 4 here, we'll get 121, which certainly factors nicely, or has a nice square root. That's going to be 5/4 plus or minus 11 over 4. That gives us 16 over 4 and also minus -6 over 4. Or 4 and -3/2. Once you have that, you can say that y is equal to c1 e to the 4x plus c2 e to the -3/2 x. I feel like I may have made a algebraic mistake here, but seems to have worked out too nicely for that. But either way, when you come up with two distinct real roots, those will give you the exponents of exponentials. So if we have 4 here and then -3/2 here, that will correspond to 4 here and -3/2 here. If you had a repeated root, you had, let's say, 4 twice, that would be something a little bit different. If you had complex roots, that would be something also a little different, but that's the general idea. Now, finding C1 and C2, in order to do that, you substitute in this information. So I'm going to, again, take this info and I'm going to move it to another page just to have more workspace. So to find C1, C2, we substitute in the initial value information. I'll move this up. And now notice we're going to want to know what the y prime is. So we will compute that here. Y prime is going to be equal to 4c1 e to the 4x plus -3/2 c2 e to the -3/2 x. And then we substitute our initial value information. So we take 1, that's equal to y of 0, which of course is equal to c1 plus c2. And then we have -12.5, which is equal to y prime of 0, which is equal to 4c1 plus -3/2 c2. And now what you can do is substitution or elimination to get c1, c2. For example, do 4 times the first one, add it to the second one. So if this is equation 1, this is equation 2. 4 times the first, add it to the second, and you'll cancel those out. So you'll get 4c2 minus 3/2 c2, which is what? 5/2 c2 is equal to you're going to have 4 times E1, then minus 12.5, and 12.5 is 25/2. So we get 8/2 minus 25/2. That's going to be -17/2 is 5/2. So C2 should be equal to -17/5. And then you can substitute back in to get C1, which I'll skip doing just for the sake of getting to other questions. But if you really want to see how that's done, just let me know and we can maybe take a look at it if there's enough interest. Another question that someone asked, can we go through a process to show that a set of functions are linearly independent. Yeah, sure. And that'll be somewhat similar to this. So notice here that we get a set of differential or set of equations, algebraic equations in C1 and C2. Then when we go through linear independence, if we're trying to show that 2 or 3 or 4 functions are linearly independent, if they are linearly independent, we'll also get a system of equations like this. And then we'll do substitution or elimination, whichever method you prefer, when it's just 2 that you're trying to solve for, 2 unknowns. But when it's 3, you really need something a little more formal. But let's go through an example real quick. So let's say you had e to the 3x and you had e to the negative 2x. And what we want to do is we want to show that these two, or this set, is linearly independent. You'll see different terminology. I haven't seen any settled terminology as far as should it be is as a set or are talking about them all. So you'll see both ways written. So show that they are linearly independent of one another, or show that it's a linearly independent set. In order to do so, what we'll start with is this linear combination. So we've got A1, A2, A1 e to the 3x plus A2 e to the negative 2x. This is not necessary, but for whatever reason, I like seeing magenta and this green together. Now we set this equal to 0. What we want to show is that no matter what, it has to be, for this equation to be true, that A1 and A2 are 0. There's no option. Now, of course, they can be 0 and the equation is true. If you just set both equal to 0, it's a true equation. That is 0 times e to the 3x plus 0 times e to the negative 2x is true. But in order to show they're linearly independent, we have to show there can't be any other A1, A2. This is the only possibility. Now, in order to do that, what we'll do is we'll substitute. We'll let x be, well, whatever you want. 0 is usually a good place to start. It won't always give you a useful equation, but oftentimes it will. If we substitute in x is equal to 0, we get 0 is equal to, now we have A1 times 1, because it's e to the 0. Then we have plus A2 again times 1, because it's e to the 0. Then from there, what we'll do is we'll let x be equal to 1, let's say. Substituting that in, we get 0 is equal to A1 e to the 3. And then we get plus A2 e to the negative 2. Now, at this point, you can do substitution or elimination because it's the way you would go about solving a system with more unknowns, let's say 3 or 4. You'd use elimination. Substitution is usually not quite sufficient to get there, or it just becomes too messy. Elimination can be nice and thorough. So what I'll do is I'll just use elimination here. And in doing so, I'll multiply the first equation, 1, by negative e cubed. So we get negative e cubed A1 plus negative e cubed A2. And then we add that to e cubed A1 plus e to the negative 2 A2. And if you add those together, what you'll get is 0 is equal to, these will cancel by design, and then you have e to the negative 2 minus e cubed times a2. That's just some non-zero number. So when you divide, you'll get that a2 is equal to 0. And then again, substitute in a2 is equal to 0, and then it's immediately clear that a1 is equal to 0. So that shows the only possibility is a1 and a2 are both 0, and thus they're linearly independent. And I'm reading in the chat, maybe someone was suggesting that homework problem 1, they got it right, but it was, I thought they got it right, but it was incorrect. And I can check that out later. I can make a note to do that. So actually, I'm going to make a note to myself. I'll reply to the person who said that, just so I remember later to check that. Like I can go in and see what you entered and see if it should have been correct or not. And I'm writing in caps just so I can find it easier later. I'm not meaning to shout at you. Okay, and another question I see is, could we do an example of higher level characteristic polynomial? So I'll actually forego that for now, just because we'll be focusing on the spring mass system for a few days, and that is going to involve just degree 2. So I think it might be just better to focus on degree 2, since that's what we'll be looking at for a while, and then look at the higher degree characteristic polynomial maybe a little later. But we'll certainly take a look at that later. Okay, so that's questions. Now let us start looking at concepts. So the big theme of today is looking at spring mass systems that are undriven. Now the undriven is going to correspond to being homogeneous. Later, when we have a driven spring mass system, that'll correspond to being non-homogeneous. In all these cases, though, what we're doing is we're looking at linear constant coefficient differential equations. And the spring mass system is just a particularly nice example. So let's look at it. Now, with the spring mass system, as a lot of you are probably aware, and even if you haven't taken a physics class, you're probably have at least heard this at some point in passing, that force is equal to mass times acceleration. And if we, let's say, have a force that can vary over time, which is possible, even gravitational force can vary over time if you're moving over time. You know, it's not always the same. When you're closer to the center of a large object, there's more gravity acting on you than when you're far away. Hence why when you get into space, you're either very light or you're weightless. But either way, the force acting on a system is the sum of all the forces acting on it. So you just add up all the different forces. Something may be pushing you up, something may be pushing you down, and depending on which is more forceful and the exact directions, you'll have a net movement or change in velocity depending on what their magnitudes are and so on. Now, for our spring mass system here, what this will amount to is this. We say that the mass times acceleration, the force on a spring mass system, where when I say this, I mean we have, let's say, a wood block bolted to the ceiling, and from this we have this spring, and then hanging on this spring is a mass. So spring mass system, hence there's a spring and a mass. Actually, let me draw that a little bit larger. Now, what's going to happen is you have a spring, and if you leave the spring be, it may have a natural state that looks like this, let's say. So the natural state of the spring may be of a certain length, but then when you hang a mass on that spring, it's going to, the gravity is going to act on that mass and pull it downwards, but then the spring is going to give some resistance. there's what's called the spring restoring force. So you have these different forces acting on the mass. You have, actually, I don't know why, but gravity seems purple to me. You have gravity pulling downward. Then you have the spring restoring force pulling upward. And eventually these two will meet some kind of equilibrium. The reason being is the more the spring is displaced from its natural spring state, whether it's either compressed or it's elongated, either way, it doesn't matter. The more it's moved from its natural state, the more it's going to exert force to try to get back to that. So if you just, and you've probably, if you've ever messed around with something that involves a spring, you've probably noticed this. If you just pull it a little bit, it's not going to resist you too much. But if you really try to stretch it out, then it will resist much more. So it's proportional to how much you're displaced away. If we call this, let's say, an x-axis, where x is the position, then as you displace, you have a bigger displacement of x, you have more resistance to that displacement. Now, there's the reason I'm bringing up this natural state and then showing this, well, one, so you can see the system, but two, it starts out at a natural state or natural length. You hang this mass, and then if you kind of let the system settle in, it'll eventually settle into an equilibrium. So there's kind of the natural spring length, and then there's the equilibrium spring length. And if you let it settle into equilibrium and you kind of gently, let the system settle, it'll eventually be totally still. And now the spring, in some sense, wants to be of this length. It has a new preferred length, if you will. So as long as it's at that length, it's not going to do anything. And well, it's trying to do something, but it effectively is in balance with the gravitational force. And when it's at that new length, that's called the equilibrium position. And we denote that by an x value position of 0. Now, the idea is that you'll either grab the spring mass or grab the mass, and then you'll lift it up from equilibrium position, like push it upward, or you'll push it downward, or you'll smack it so that it all of a sudden starts moving from its equilibrium position, like hit it so it goes upwards, or hit it so it goes downwards, either way. And from there, it'll start to exhibit particular type of behavior. And that behavior is to oscillate about the equilibrium position. Now, as it's doing that, there are two forces in particular acting on it. Now, the gravitational force has reached an equilibrium with the spring restoring force. So those kind of cancel out when it starts in this equilibrium position. But then from there are two additional forces, and one is actually the spring restoring force again. So the spring restoring force will, from then on, since we in some effect kind of canceled it out with gravity, it will then additionally act to try to restore this whole system to its given length. And just like with its natural state being stretched out to the this like equilibrium state, it's going to resist more as you get farther away from equilibrium position. To represent that, we say negative k times x, where k is something that's positive, and x is, again, the position. So if you give this thing a big displacement from 0, here, if it's at 0, there's no spring restoring force additionally beyond the one that's resisting gravity. But if you give it a big displacement, this will be a large force here. And it will always try to displace you back to equilibrium. So if you, and let's say this is positive x, and this is negative x, It's usually how they do it, but you can set up your own coordinate system. If you, let's say, move it upwards, so you have, how do I want to say it? Let me draw maybe this. So if you have the spring and it's here, and you have a position of, let's say, x is equal to -2. Well, when x is equal to -2, if k is positive, then you'll have this force is positive, which means that it's trying to send you back down this way. That's what the spring restoring force is doing. And likewise, if you then have something positive, like you have, let's say, the spring, sorry, it's getting a little abstract with the drawings here, but if you displace it positively, let's say now your x is equal to 3, then you have -k, which is positive times 3, so it's a negative number. It's trying to push you back in the negative direction. It's trying to push you back upwards. That's how the spring restoring force works. Now, there's one other force that's acting on this, and that is the damping force. So you can think of this as the internal resistance of the spring, the fluid that it's moving through, all the forces that would create natural damping or resistance on the system. Probably the best way to think about it is the fluid force, like the fluid resistance acting on the system. You know, when you drive a car, you have air resistance on your car, which means you have to spend more fuel, more energy to, keep up your speed. If you try to swim, you'll notice that, it takes some work to actually move through the water. So this is because the fluid, either the air when you're driving or the water when you're swimming, resists your motion. It's the same thing here. Now, there can be different causes of resistance, but in general, there's going to be some what we call damping. And this is c times x prime. The faster you drive a car, the more air resistance there is. In fact, it's kind of interesting with that because it's linear for a while and then it becomes quadratic, which is very, very strange. I don't know why it would change, but it's kind of cool. At any rate, it resists your velocity. The faster you move, the more it's going to resist. So there's the farther you are from equilibrium, the more it resists. Here, the faster you move, the more it resists. And this again, where c is greater than 0 and x prime is the velocity. So there's resistance to how far you are, and then there's resistance to how fast you're going. Now, if you just do a slight rearrangement here, what you get is m x double prime plus cx prime, because I'm going to add this to the other side, plus kx is equal to 0. Now, notice I said undriven. Later on, we'll see driven, and driven means that you have an additional, let's say, motor or something injecting energy into the system that's also disturbing the system from its natural state. But the big thing we're going to look at is this here. Now, since we have this, we can get 4, maybe 3, depending on how you classify it, different types of motion. Since we have m, actually, let's save that for over there. Since we've got mx double prime plus cx prime plus kx is equal to 0, this is linear, it's constant coefficient, and it's homogeneous. And we know that in such a case, we have a characteristic polynomial, which would be mr squared plus cr plus k. That would be our characteristic polynomial p of r. Now, if we want to find the roots of that, there are 3 different cases. Well, actually, maybe 4, depending on how you classify it, but certainly at least 3. And the different cases are, you could have distinct real roots, maybe an R1, R2. And if you have that, your position function, you can tell you have position x at time t is equal to C1 e to the R1 t plus C2 e to the R2 t. That, if you were to graph such a thing with different values of C1, C2, what you will find in general is it looks like this. And I'm going to need to leave myself enough room here. Let's see. Actually, let me jump to another page. Okay, so we have distinct real roots. I'll divide this into quarters here. Gives this solution. And I want 4 areas. That should do it. The distinct real roots, if you were to graph this, and maybe I'll say green. If this is the t-axis, this is the x-axis. Then what this looks like is roughly, again, it'll depend on your C1, C2, but the rough behavior is something like so, where it kind of is horizontal for a little bit, then it drops off, and then asymptotically approaches the t-axis. If you look at the case where there's repeated real roots, so let's say you have R one time and then R again, because we know by the fundamental theorem of algebra that we're going to have 2 roots, but there may be some repetition. We'll have x of t it's very similar to distinct real roots, except we have, actually maybe this is a better way to show it, C1 plus C2 t times e to the RT. If we go ahead and we graph this, what we will get, now it's going to look very similar to the distinct real roots, but what I'm going to try to do is make it seem like it drops off faster. So they look similar, but there's a faster drop off in this case. The other 2 cases, which you could classify one as being a subset of the other, but you could have complex roots, where you have and now I definitely want to color these differently because it really impacts what happens. So let's say we have A plus, and I'll do B or beta, alpha plus beta. And actually that should be minus beta. There we go. If you have these 2 complex roots, then your solution, which maybe I'll do in yellow, is going to look like this. And I'm going to need a lot of room for it. It's going to be C1 e to the alpha t times cosine of beta t and then you have the same thing, C2 e to the alpha t sine of beta t. And now I'll draw it in yellow. If we look at it, and the reason I really wanted to distinguish the real and the imaginary part, the alpha and the beta, is because the alpha is going to depend on how it's going to influence how this decays. So you're going to have something that looks kind of like this. And that alpha part, or the e to the alpha t, that's going to give you a decay. Now, why do I say decay? It could either be a decay or it could sort of blow up. It could expand the amplitudes. The reason it's decay is because this alpha will end up being negative. And why is that true? Well, let's think about what we're looking at here. We're looking at this equation, mck, and if we use the quadratic formula, it'll end up being that alpha is equal to negative c over 2m. Since c and m are positive, that means that this is negative. That's why you get a decay. You get e to a negative number times t, which gives you decay. The only other possibility is if c is 0. So this does assume that c is greater than 0, which in general, it'll be greater than 0 or it could be equal to 0. Now, the last case is essentially a subcase of complex roots, and that's if you have purely imaginary roots. That is, you have, let's say, I'm just going to grab the beta i's here. If you don't have a real part, you just have plus and minus beta I. In that case, you're going to have a solution function that is C1 just cosine of beta t plus C2 sine of beta t. There's no decay terms anymore, or decay factors. So you have this. And what that amounts to is just what I'm calling natural oscillation. That is where there's no decay. And essentially there's nothing to keep it just from oscillating forever. That would look something, let's see if I can draw it well. Something like this, where you'll notice we just have this constantly, I don't know if orange is the right one, but we have the amplitudes not changing, unlike here where they decayed. And now what we call this, or call these different cases, is based on damping, as I've indicated here. We call this one, the last one, we call this undamped. And I should put this in a color to make it really clear what we're talking about. Let's do this. So this is undamped, where the damping really comes from both, and I'm going to flip back to the other page. It comes from whether this C is 0 or not, and then after that, what is the relationship between these two things? Or between these three things, rather. What their relationship is comes out through the quadratic formula, which depends on what kind of roots you're going to get. When you do the quadratic formula, what you'll get is that R is equal to negative C over 2m plus or minus 1 over 2m times square root of C squared minus 4mk. You're going to get this. And depending on what this number is and this number, it'll give you these different types of roots. But rather than just memorizing that, oh, we have to look at this formula, it's really just what are your root types? Your root types tell you what your solution is going to look like. And that decides everything. So whether you look at this or look at your final roots, it's exactly the same thing. It's just how you're choosing to make that connection. But either way, if C is 0, you won't get any value here. Like that'll be 0. And then here we'll have zeros. And M and K are positive, so you get square root of a negative number, so you'll get imaginary only. So once C is 0, it forces you, in this case, to have imaginary roots. And we call that undamped. There's no damping. Now, a good question is, will the shape of the graph be the same regardless of the numbers? The general shape, yes. So for example, if you have purely imaginary roots like this, in general, you'll have this shape, though it could be shifted a little bit, left or right. That is, and let me know if you can't really see this. Hopefully this is big enough. But you could also have something like this, where it looks, should draw that a little bit thicker, where it looks like so, where you don't start at, the maximum amplitude, you start maybe a little lower, and then maybe you start actually going downwards. All that will depend on what the initial value data is. But the general shape, yes, will be the same in each of these cases. It'll just maybe be shifted, or the amplitudes might be a little different. You could have a case where maybe the amplitudes are kind of like so. But the general behavior and shape will indeed be the same. In the other cases, what we call them, since there is still oscillation in the complex roots case, we call that underdamped. The idea being that there's damping, but it's not enough to prevent the oscillation. There'll be decaying oscillation, but there still is some. So it's not damped enough. That's where the underdamped comes from. Not quite damped enough to prevent oscillating. So there's infinite oscillation in this case, even though that there's decaying in the amplitudes. Then we go from underdamped to a critical position or critical relationship between these values. If it ends up being that this is 0, essentially that's a turning point from being underdamped to what this will be, which you could maybe guess, but hint, it's overdamped. There's a kind of in the middle spot called critically damped. It's where you go from having this discriminant value 0, which gives you complex numbers, to having this value be, I'm sorry, you go from having this value be less than 0, which gives you the complex numbers because you get an imaginary part, to being 0, which is where you get critically damped because then this whole term is 0 and you get a repeated root, to then going to having this be positive, which gives you the 2 distinct roots. So this really decides whether you're in the first case, second case, third case. C itself also decides whether you're in the undamped case. Now you go from underdamped to critically damped to what's called overdamped. The reason or the idea there, the intuition is that if you, let's say, open a door and then let it like swing, and let's say it's like a double hinge, or in any case where there's oscillation behavior, how doors usually work is, well, besides not having a double hinge, they don't swing back and forth. You open it and then it slowly closes on its own. That's like a door opening. Like this is the door being really open and then it slowly comes to a close, but it doesn't swing past being closed. One, because of the prevention of the physical shape, but also two, even if it could, there can be enough damping so that that doesn't happen. So there's overdamped, critically damped, underdamped, and undamped. And I want to check a question someone had. So the question is, later when we have something injecting more energy into the system through like a motor or what have you, some driving force that we add to it, you will have potentially somewhat similar behavior. For example, you could have something like this, but in fact there's resonance, and instead of decaying, you could have it actually like blow up. And there's actually several real world physical examples of that. Or you could have something like this, but you have some sort of kind of extra wiggle in the waveform. Actually, this is how you get, sound in music. You take various wavelengths, you add them together, and you get new wavelengths that look kind of funky like this, and that's how we hear, different interesting sounds and so on. Right. But let's actually get into some other terms and kind of run through some examples. And notice I put a lot of examples, but I'm not too worried if we don't get to all of them. Once we do one, they're really essentially all the same. The most important thing is to understand the difference in these cases. That's the big thing. Now, in addition to this, you have some notions of period and frequency, and I've essentially written it as period frequency and then pseudo period, pseudo frequency. Maybe I'll actually start with pseudo period and pseudo frequency because period and frequency are just a more specific case of that. So let's say you have an instance where there's oscillation, either in the undamped or the underdamped case, either one. Because it's a little more general, let's do the underdamped. Say our waveform looked like this. Okay, so say it looks something like this. The period, and let me again highlight that this is the t or time axis. This is the x or position axis. The period is simply how long it takes to go from one peak to the next, in short. So we have a peak here, we have a peak here. Let's make that a little brighter. Have a peak here, have a peak here. How long in time does it take to go from here to here? This would be, in this case, what's called the pseudo period. Time it takes to go from peak to peak. When you have a waveform or have a wave like this, there's actually oscillation. You would not talk about period and frequency when you're looking at the cases of underdamped or critically damped because there's no oscillation. So these terms don't make sense. Only when you're underdamped or you're undamped do we talk about these things. So the pseudo period is how long it takes to go from peak to peak. That's going to be measured in seconds, obviously, because you're measuring over time. So period, pseudo period, these are in units of seconds. And if we call the pseudo period, let's say capital T, the period T, I don't know if there's maybe different notation for pseudo period, but it's not going to be important for us. The concept isn't more important than the notation for that, for distinguishing these two. But once you have that, you can get a notion of frequency or pseudo frequency. And again, pseudo is just applied in these cases where you have some damping. So if we had undamping, we would talk about period, or if we had undamped, we would talk about period and frequency. And if we have underdamped, but not undamped, then we have pseudo period frequency. So this is undamped. And what was this, yellow? And this is the case of being underdamped. But the idea is identical. Whether you are going from peak to peak and those peaks change in height, it's still peak to peak. So really, in my opinion, this is a little unnecessary terminology, but this is what you'll see. So I want to make sure you're aware of what's going on here. I want to check the chat real quick. Okay, covered that. And pseudo period is what we call lambda in physics. Is that true? I'm trying to remember. I thought, was it something like this? I can't remember the notation. offhand. Yeah, wavelength sounds right. Yeah, that sounds right. Because you're looking at, yeah, essentially how long it is. Because the only way to measure the actual length of this is by measuring a part of it. Yeah, so I believe that would correspond to lambda in physics notation. Okay, so this is our t here. Now the frequency we'll denote by just a little f. And you may know from your other classes that the period is equal to 1 over the frequency, and therefore the frequency is equal to 1 over the period. What this is how many times you're going to go through a cycle in a second. If, let's say, this is 1 second, the number of cycles you go through in this 1 second, supposing it is a second, so I can write second better than that. The number of cycles that you go through in the second here, well, the second starts at the bottom. We go up, get back to the bottom, so that's 1 cycle. And then we go from the valley here, or the bottom, back to another valley. So we've gone through 2 cycles. So supposing this is 1 second, this waveform goes through 2 cycles in 1 second. So the frequency would be simply just 2. It's cycles per second. And that's commonly used as, or commonly denoted as hertz, which you've probably seen in media talk about refresh rates of televisions and monitors and so on. Okay, so let's now get to the following. All right, an overdamped system. But really all of these, I'm not going to get to all the examples I had posted originally, but they're just going to be the same type of problem over and over again. So if we have this system, I'm even calling it overdamped, but let's see that it for sure is. We have that it's linear, constant coefficient, homogeneous. That means we can find a characteristic polynomial. That means that we have a polynomial like so, 3r squared plus 3r minus 6. That'll factor. We can factor out the 3, r squared plus r minus 2. I'm going to do this a little fast just for the sake of time to make sure we get in 1 or 2 examples. That's 3, and this factors nicely as what? R plus 2, r minus 1, right? So we have roots of r is equal to -2 and r is equal to 1. That tells us, since we have distinct real roots, we're going to have a waveform, or sorry, not a waveform, we're going to have a solution that looks like this, c1 e to the -2t plus c2 e to the t. Now, this will not have a period or frequency because there is no oscillation here, or there's no infinite oscillation. Sometimes we'll have a case where, and I thought this was a homework problem, I can't remember, but you might have something that's kind of like this. It swings past equilibrium, but then it never comes back. Or if I remember right, you'll do a homework one where you can get it to like, swing through 1, 2, 3 times, and then approach asymptotically. But so you can get it to do a finite number of times, if I remember right, but you're not going to do it infinitely many times. The only case where you talk about pseudo frequency and period is when you have a cosine and sine. Otherwise, we don't have any way of determining what the overall frequency and period will be. So these terms will not apply here. Now let me jump to critically damped. This problem is going to be essentially exactly the same, except you'll see something like C2t e to the whatever times t. So I'm going to skip this one because it's really the same as example 1. Now underdamped, let's do the following. Let's do x double prime plus x plus 8, or plus x prime plus 8x is equal to 0. Yeah, this should do it. Now, this will have a characteristic polynomial. That is the polynomial r squared plus r plus 8. I'll use the quadratic formula on this. That'll give us r is equal to negative 1/2 plus or minus 1/2. And I've chosen this, so hopefully we get something that's a complex number. And we get 1 minus 4. I could choose this to be nice. It doesn't really matter. 4 times 8. I was going to try to rewrite it to choose like a nicer value, but it's not worth the time. So we get 1 minus 4 times 8. So we get negative 1/2 plus or minus 1/2 square root. And what is 4 times 8? Should know this. 1632. So negative 31. So we get negative 1/2 plus or minus root 31 over 2 times I. I'm going to check chat really quick. Will these always be in a sine wave form? So when you're underdamped or you're overdamped, or I'm sorry, when you're underdamped and you're undamped, you will have, you can think of it as a sine wave, just shifted a bit. So a sine wave, if we just look at sine as like this, cosine is in some sense a sine wave because we just shift it to go from sine, like this is x is equal to sine of t, and this would be x is equal to cosine of t. So you can think of it as just a shift so that we start out at 1, but otherwise the general shape is the same. So they're all sine waves in a sense, at least when you're in the undriven case. When you're in the driven case, you might have cases like this, where the amplitudes grow, or you may have weird things kind of like this. And those are not exactly sine waves, but they're combinations of sine waves. So yeah, all of them are going to be either sine waves or combinations of them, where when we say sine waves, we mean that they can be translated. And another question is, in an underdamped system, will each pseudo period have the same length? The answer to that is yes. Yep, the pseudo period is the same, which is one of the reasons it's such an important thing, is because you can tell how the system's going to act completely just by knowing the period. It's always going to have that same period and the same frequency. And we'll see that here. Okay, so what's happening? We've got these two roots. Now there's going to be, forgive me for not coloring for the sake of time, but there's going to be a real part. If you guys really want the color, let me know and I'll add it. But we have C1 e to the negative 1/2 t cosine root 31 over 2 t. And then C2 e to the negative 1/2 t sine, and I got to give myself some room, sine of root 31 over 2 times t. And actually, I can't even resist it. I do want to color these just because I think it makes it much easier to see what's going on later. Like once you see the connection, it's just very clear how this should all be arranged. And let's color that maybe blue. Okay. Now the blue, or the real part, that's going to be the decaying envelope. So we're going to have oscillation here, and the decay is going to be determined by the blue. So I'm going to draw in blue here a decaying envelope. Now notice we haven't solved for C1, C2. Only if you solve for C1, C2 can you decide exactly how this is going to look. The envelope is going to be the same regardless. I don't know whether we're going to have this waveform or we're going to have this waveform. You see where I start out, it totally depends on the initial value conditions. I haven't specified those at the moment. I just want to show you how the period and frequency works, in real time here. Now think about cosine. think about cosine, and this is going to be a question for you guys, and hopefully you can just give me an answer relatively quick, whether you know or not, just to see where you are. Cosine of x. Can you guys tell me or give a guess offhand? What is the period of cosine of x? You just type it in chat to see where you're at with this. How long does it take cosine to go from its height, a peak, to another peak? Just whatever you think. I'm not judging you whether you get it right or wrong, just to see where you're at. Okay. Yeah, interesting. So a number of people put pi. In fact, and I can totally see why you'd put that. In fact, it's twice that. If you do pi, you'll go from -1 to, or I'm sorry, you'll go from 1 at 0. Here is pi, you'll go to -1. To get back up to the peak, you actually need 2 pi. Yeah, so you're going from peak to peak, but I totally see why you might say pi. Now, if that's the case, though, it takes 2 pi time to go from one peak to the next peak, to go from here to here. Then what that means is we take this thing, which is square root 31 over 2 times t, and in order to find the period, or the pseudo period, pseudo in this case, but I may be a little lax on the terms, think of that in the same way as regular cosine. It takes 2 pi to go through a period. So in that case, t, which I'll change to capital T here, should be what? It should be 4 pi over root 31. So that's the period here. In order to get that, all I did was I set this equal to 2 pi, because that's how much regular cosine and regular sine take to go through one cycle. And now if you want to find the frequency, just need to remember that that's the reciprocal. So the frequency is root 31 over 4 pi. And again, what this looks like exactly will depend on what the initial conditions are, but it's going to be kind of something like this. Or I'll actually just draw another one so you can see it's not always going to be exactly the same. It could be something like that. So here are some potential waveforms. What they are exactly will depend on the initial conditions. Okay, with that, I'll be around till 10:15. Otherwise, I hope you guys have a good day, and we'll see you on Friday. And I see someone pointed out that it's locked that one of the assignments is locked till PM. Yeah, that probably was just entered as PM instead of AM. I'll change that now. So that's assignment 13. Let's change it from, yeah, it was just a typo. Okay, it should be changed. So assignment 13 should be available now. And I see another question, but let me just save something really quick. Okay, Corbin, you were asking about, are we going to start these underdamped problems, or just in general undriven problems today? Yep. Yeah, we are. I'm looking at day 13 now, and it has, classifying the systems, are they underdamped and so on, and then looking at the frequency. Okay, so you're asking if we have a starting point. Let me see. Yeah, let's see how that might affect things. Let's do this last example. Actually, I'm going to cut the recording. Actually, no reason not to keep recording. So we have, let's say, x double prime plus 4x is equal to 0. And then we have x of 0 is equal to 1. And if you guys would, if any of you hear me and can remember, to remind me to actually say something about angular frequency, because I realized I forgot to mention that. It's a very simple thing, but worth mentioning. Okay, so let's say we have this system, its initial value problem. If you go through and you find the solution, maybe I'll skip that unless you really want me to go back through it. But long story short, you're going to get C1 cosine of 2t plus C2 cosine of 2t. From there, you can use initial value information to decide what C1, C2 are, just like before. If we do that, we're going to need to know x prime, which is going to be negative 2c1 sine of 2t plus, oops, I wrote this as cosine twice, but that should be sine. We're going to have then plus 2c2 cosine of 2t. And finally, x double prime will be negative 4c1. Actually, no, that's all I need. Now we substitute in x of 0, which is 1, meaning we have c1 times cosine of 0 is 1, sine of 0 is 0. So we just have 1 as c1. And then in the second case, we have 0 is equal to x prime of 0. And then in that case, we have 2c2 is equal to 0. So with this set of initial value data, we get that C1 is 1 and C2 is 0. Now, as far as the physical system goes, what this amounts to is the following. Well, if x is the position and 0 is the equilibrium, what that means is we've got our spring mass and there's an equilibrium, let's say here. That's the state the spring mass system wants to be in if there's no disturbance in it, if it's just gravity and the spring restoring force canceling each other out or balancing out. And then in this case, at time 0, we have a displacement of 1. So this would be a positive displacement, plus 1. At that time, we have a velocity equal to 0. What that means is we essentially have it at rest, but displaced from the equilibrium position. This would be as if we took the mass and we pulled it downward, and we just held it in place, and then we let it go. Once we let it go, it's going to try to pull itself back to equilibrium, but then it's going to sort of overshoot, and it's going to sort of go back up and then go back down and so on. Like if you were to take this spring mass system, what this will amount to, and actually I want to draw a bunch of small pictures. If here's equilibrium, and here's, let's say, time, and time is equal to 0, you're going to start out, and it's going to look like this. And then at some time a little bit after that, it's going to start moving upward. Then you're going to have, eventually you pass through here, but you're still going to be moving upward. In fact, you're going to be moving even faster upward. That's going to cause you to overshoot it, or cause the mass to overshoot. Now you're really sort of like so. Then eventually you'll stop. And then after that point, you'll continue backwards. So you'll start to push back down. And that's what causes the oscillation. So you get something that looks like this. And it'll just oscillate back and forth. And now in this particular case, we found out that C1 is equal to 1, C2 is equal to 0. So what that means is that this solution is going to be C1 is 1, C2 is 0, so it's just cosine of 2t. And that would be this magenta here. Now it's drawn like this because I'm just trying to show how it matches up with these diagrams. But if you actually take this and graph it, it'll look, of course, something like so. Oh, don't want that. It'll look like this. And then we can find the actual period just by seeing how long it takes to go from peak to peak. And that we take to be 2t is equal to 2 pi. And thus t is equal to pi in this case. So it takes pi seconds to go through one period. It took 2 pi for normal cosine, and this moves twice as fast. And notice this is kind of the upside down version of this because we have positive going in this direction, like the positive axis is like this, where here it's going upwards.
To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.